This is the last question. It is about measurement error. So suppose that we are interested in estimating the production function, right? And we assume that the production function follows the Cobb-Douglas form. And we observe many firms indexed by I, and they share the same production function. And and under the assumption that like the outcome y and factor productivity a, labor input L, capital input K are strictly positive, we can take the log of those variables and we will change the uppercase letters into lowercase letters like this, and they are logged variables, and then it becomes well-known linear term. Here, what we observe is the output y and labor input L and say K. Later, there is some problem with the capital, but anyhow, and the factor productivity A is unobserved. So we will decompose this into intercept, which is the mean of the productivity, and the disturbance term, which is the remainder, right? So it becomes the well-known linear regression form, right? An additional problem here is that, excuse me, in many cases, the capital input K is not directly observed, or there is no one single correct measure of capital, right? Depending on how you do the accounting, the capital input or the total amount of capital could be different. Like for example, there are many different ways to account, like take care of the depreciations, right? And like inventories, things like that. So we are going to assume that what we observe is not the direct capital input, but we observe a proxy variable for the true capital, right? K is the true capital, but H is like some measure of capital input on the book, like financial sheets, right? So, and we assume that H, observed H is true capital plus measurement error epsilon, right? I'm sorry, excuse me. The measurement error epsilon is, of course, mean zero, we assume, and it is pure error, measurement error, so it is uncorrelated with everything else, right? So epsilon is uncorrelated with like output, capital, and true and labor input. Okay, so we have addition. I didn't mention this. W, the error term from the factor productivity, is uncorrelated with both inputs. So there is no endogeneity problem in this if K was observed. K is exogenous, right? But let's think about the measurement error. So first, show that we have to write it this way. So because K is unobserved, we have to use H instead of K. So then here, there are actually two true models. True models are Y so if K was observed, then we could use this one. But another is about H, right? These are two truth. So based on these two truth, but you are estimating Y on L and K. And from the first equation, I'm going to add and subtract plus epsilon. I will add epsilon to K and then subtract the same amount. Okay, then as you can see, this much is the new error term, which is denoted as psi. So, and we know this is H. So as a result, if you plug this in here, we know Y is alpha plus beta L plus gamma H plus psi. Okay, that is part A. Question B. Derive the misspecification bias in beta and gamma if you estimate the regression with H in the place of K. I didn't answer this. Let's show that H is correlated with psi. So the correlation, the covariance between H and epsilon, psi, psi can be written as covariance between K plus epsilon and U minus gamma epsilon. All right. So then let's think about this. You expand the covariance between K and U plus covariance between epsilon and U minus gamma 0 covariance between K and epsilon and minus gamma 0 variance of epsilon. Right, as you see, we can divide this covariance into 4 terms, and this is 0 because we assumed K is in the exogenous, and this is 0 because epsilon is measurement error that is uncorrelated with everything else. And this is also 0. The measurement error is not correlated with the true capital. It's purely white noise. So the 0, 0, 0, simply we get this. As long as variance of epsilon is not 0, so if variance of epsilon is not 0, right, and gamma is not 0, then the covariance between H and psi is not 0. And these two conditions are pretty trivial, right? So measurement error is non-zero. The variance of the measurement error is not 0. Otherwise, we don't have any problem like this. Like K is observed. So it's kind of obvious from the setup. And gamma is not 0. That means the capital input has some effect on the output, which is also natural assumption from the economic theory, right? So as a result, we can show that covariance is not 0. So in this equation, H is endogenous. A new problem happens. Even if the true K was exogenous, but its measurement error, its proxy variable may be endogenous. That's the problem caused by measurement error. So now then I will think about the misspecification bias caused by the endogeneity. So let me write X for L and H, and similarly, like theta is for beta and gamma. And for now, I will assume that everything is demeaned just for algebra, right? So I will ignore the mean and the intercept. So theory does not change at all. And under the wrong assumption, under the misspecified assumption, you believe theta 0 equals expectation xi transpose inverse times xi times yi. This is what you get if you make a wrong assumption. But in true model, I will calculate the estimate, especially I will think about this. This guy, y, can be written as xi times xi transpose theta and psi here, right? As a result, we get it's x prime times theta plus expectation xi psi. So now then, so expectation xi transpose inverse expectation xi yi, then we get like the first term simplifies to theta 0 after you multiply the inverse, plus we are going to have undesirable term like this, okay? So as you can see, this is the misspecification bias. let me calculate, do the algebra. So expectation xi transpose equals expectation L squared, expectation LH, expectation LH, and expectation H squared. Okay, and then its inverse equals 1 over expectation L squared, expectation H squared minus expectation LH squared. Okay, so the denominator is the determinant. Right now we are not going, I don't care about them. HI squared minus LH minus LH and L squared. So this is the inverse. On the other hand, x psi equals, it was 0 times minus gamma 0. Let me write sigma epsilon squared. This is the variance we calculated. We calculated the variance like this. So I'm taking that here. Then now let's multiply them. And what you get is 1 over determinant. Let me just write it as just determinant. And the first term is 0. So it is pretty simple. Above we get gamma 0 sigma epsilon squared times expectation LH. That is the misspecification bias for beta, and for gamma, this is the misspecification bias. Okay, right. So now then, let's think about this. Let me see if it's right. Okay, so then what, let me see, this is misspecification bias in beta 0, and this is for gamma 0, right? Misspecification for gamma 0. And first, the bias in beta 0 depends on gamma and epsilon variance and covariance. This is covariance between L and H because we assumed everything is demeaned. So if covariance was 0, then beta is not affected. If the labor input and the capital input were uncorrelated, then the problem, the endogeneity problem in the capital input does not go toward the labor input, labor coefficient. However, if here we expect some covariance from there. And also here let's think about gamma. So if gamma is positive, then this is positive, this is positive, this is positive, then it is negative, right? Then bias is negative. But if gamma was negative, then negative, negative, positive, positive. So the bias would be positive. This means, right, if gamma was positive, it is biased toward 0. If gamma was negative, it is biased toward 0 in both sides, from both sides. So we call this attenuation bias. Just we like always the bias is going toward 0. That makes the effect of capital as like weaker, right? So it is intuitive because, so think about this. In the capital, there are noise. In the capital measures, we observe noise within it, which and the noise, the measurement error does nothing toward output. It's not productive, right? So it looks like as if capital is not doing any work, right? So the coefficient of capital is estimated. The magnitude of the coefficient is underestimated, closer toward 0. So that was answer to B. Okay, and of course, usually I expect gamma is positive, so it'll be underestimated, right? But in general, measurement error causes an attenuation bias. Finally, so I'd like to show that another proxy variable can work as an instrument. By the way, we just did B. Right, we just did C. There we have done both. So let's think about D. So here we have another proxy. Now there are three true models. We assume sorry, it should be K. Here should be K. So this is the first true model, and second true model H. And the last true model is G. Okay, so based on this, and here L, K, U, epsilon, eta are all uncorrelated with each other. So all of them are uncorrelated with each other. And we learned we are going to regress Y on L and H. But the error term becomes Xi, where Xi is defined as U minus gamma epsilon. Okay, so then we learned H and Xi are correlated through epsilon. That makes it right. So that's intuitive. And now I'm going to show that G is a valid instrument. So we have to check two conditions in this simple case. First, IV exogeneity and instrument relevance. We need these two conditions. Okay, so IV exogeneity means covariance between GI and Xi should be 0, right? And the relevance in here means expectation of Xi, Zi in general has full rank, right? And in our case, X is L and H, and Z is L and G. All right. So let me derive the exogeneity first. Exogeneity is pretty simple. Gi Xi I is covariance between K plus eta and Xi is Ui minus gamma epsilon. I assume that everything is uncorrelated with right? So K and U are uncorrelated because K is exogenous. Eta and U are uncorrelated because eta is just another measurement error. And K and epsilon is uncorrelated because epsilon is pure measurement error. Similarly, eta and epsilon is also uncorrelated. Both are just different types of measurement errors. They are uncorrelated. That's our assumption. So this is 0, right? So you can expand it. There are 4 different terms, all 0. And now let's think about XZ transpose. That is expectation of L squared and expectation L and G and expectation L H and finally L H G. This is the 2x2. I forgot to say that I assume everything is demeaned. Assuming that L, H, and G are all these 3 variables are demeaned, then we just need to show that this is full rank. By the way, so actually we had to have a constant term as a third term, but we will ignore that by demeaning every random variables. So for this to be invariable in this case, for this to be full rank, that means it is invariable. that means we have to assume that this is not 0, right? This is not 0. So this is the condition we need. And let's think about it. Can you say anything more about this? I'm not sure. So this expectation HIGI is expectation k plus epsilon times k plus eta. It will end up as like expectation k squared, okay? Because epsilon, eta, and k are usually uncorrelated, okay? So similarly, expectation LGI is expectation LK plus eta. That is also expectation LK. Expectation LH is expectation L times k plus epsilon, which also equals k like this, right? Then in the end, if you plug these guys back into here in these three terms, then we get expectation L squared expectation k squared minus expectation LK squared. That should be different from 0. And you know, this is actually the same full rank assumption for the original equation, right? Back to the original equation like this. If you assume a full rank assumption here, then that will also imply the relevance condition for the instrument. When you use another proxy variable as an instrument, then it will satisfy the full rank assumption for the instrument.